Alright guys, welcome. We have our second video lecture here. This is about energy, and I know we started reviewing energy on Friday before break, but this is going to add something new to the picture, so don't worry, I'm not just reviewing. It's not only it's not a waste of your time if you totally understand energy. So with that in mind, we have a few important equations on this slide right here. We could see the equation for the potential energy of a spring, and the potential energy of a spring, which is the elastic potential energy, is equal to 1/2 kx squared, where we have k, the spring constant, and x, the displacement of the spring. And so, effectively, when you have a mass spring system and you know that the spring is stretched or compressed, then you know that there's going to be potential energy stored in that mass, I should say in that spring, and that potential energy is equal to 1/2 kx squared. So when you solve energy problems with mass spring systems, you should expect to use this equation for sure. With that said, the pendulum's a bit different, of course, because there's no spring involved in a pendulum. So if we look down here, we'll see the equation for the pendulum potential energy. So when we have a pendulum, the pendulum, of course, swings back and forth, okay? So we have a pendulum here, and it's going to swing back and forth along a path there. And the point is that with the pendulum, there's no spring, so the potential energy is stored in the gravitational field of the Earth. And so we see a familiar equation here, mgh, mass times 9.8 times the height of the pendulum for the potential energy of that pendulum. Now that is, as I said, very familiar to you guys, and it shouldn't be anything new. So the question is, okay, so, what is the new information in this energy lecture? And the answer revolves around this term here, and that is the height of the pendulum. Because if you remember, when it comes to a pendulum, we have this little bob at the end here, and we measure the displacement of the pendulum, theta. And so usually you're going to know theta, but you're not going to know the height of the pendulum. In other words, you're not going to know whatever the h value is right here. So even though the pendulum swings back and forth, it's not usual for for you to know how high the pendulum goes. In a physics problem, most often you'll have the displacement, the angle of the pendulum. So then the question becomes, okay, so if I know that angle, how can I calculate the height of the pendulum? Because that is, after all, what we really need. We need this h term. And so most of this lecture, in just a moment, we're going to get started on exactly how to figure out this height term for the pendulum so that we can calculate the potential energy for that pendulum. And before we get to that, I just want to remind you, of course, that in both mass spring systems, so this applies to both here, we do have, of course, our kinetic energy formula, which is 1/2 mv squared, which should be very familiar to you. And so if I have a mass spring system, when that mass is in motion, it's going to have kinetic energy 1/2 mv squared. But it also applies to the pendulum. If I have the pendulum swinging back and forth, when that pendulum is moving, I'm going to have a kinetic energy of 1/2 mv squared as well. Okay, so a few reminders down here. If you look, we have mechanical energy being the sum of kinetic and potential energy. Very important for us to remember that. And of course, if we have no friction and no air resistance, then we can say definitively that the mechanical energy is going to be conserved, which means that the initial mechanical energy will be equal to the final mechanical energy. And of course, we can expand upon this equation right here. By being more specific, we could say, well, this mechanical energy right here is going to be equal to the kinetic plus potential, and the final mechanical energy is going to be the final kinetic plus potential. So all of that can be, written out like that. And then, of course, let's remember that we could, for the kinetic energy, we could substitute in this expression right there. And that is important to remember. And then for the potential energy, of course, we could do something similar with mgh up here, could, go in here. So you would just have to plug in the appropriate equations when needed. Okay, so we're going to go ahead and take a look at the pendulum here, and we're going to try to figure out the height of the pendulum based upon the angle theta that's given. So, as you can see here, we have our little cosine equation written out. That's going to come in handy in just a moment. You'll see why. So, effectively, we have to ask the question, if the pendulum has a displacement theta, then what is the height of that pendulum? How much height has that pendulum gained, okay? So, we can do a little geometry here to answer that question. I'm going to show you guys how this works. So, I'm going to draw a horizontal line right here real quick. It didn't quite come out right. Let's do that again. There we go. And so this kind of gives us some understanding of the height of the pendulum, the height that the pendulum gains as it swings back and forth, keeping in mind that this right here is the same as the length of the pendulum. That's very important because, of course, this is the length of the pendulum, but when the pendulum is in the equilibrium position, this is the length of the pendulum. It's the same L, okay? So once we recognize that fact, then we also see that we have this H right here, and we can begin to do a little bit of geometry, but first, we need to figure out an expression for X that is going to be useful. In other words, we know X plus H is going to be equal to L, right? Hopefully that makes sense to our brains, right? So with that in mind, we just say, okay, well, let's go ahead and solve for X. If I do that, then I'm going to get the expression L minus H, which hopefully should make some sense to us. So once we have that, we're going to go ahead and come in here and actually replace X with L minus H. We don't need that anymore. And now I can start to use some trigonometry because I have 1, 2, 3 pieces of information about my right triangle right here. And so once I have those 3 pieces of information, I can go ahead and begin to use the cosine function. And in fact, we do know that we have to use cosine because we see the angle, we see the hypotenuse right here, and we see the adjacent side right there. So how are we going to relate the adjacent and the hypotenuse? Well, that's going to be with SOHCAHTOA, we use adjacent hypotenuse, cosine, okay? So once we have that in mind, and we're going to go ahead and erase this guy down here, we can go ahead and write this out. Cosine of the angle is equal to the adjacent side. Well, what's adjacent to theta here? It is L minus H, so we can write L minus H right there. And then what is what's the hypotenuse rather? That is L. So if we write this cosine function out, we can begin to get an expression for the height of the pendulum. All we have to do is solve for H. So moving down here, we're going to go ahead and multiply both sides by L. So you end up with L cosine theta equals L minus H. And then we can go ahead and subtract L from both sides. L cosine theta minus L equals negative H. We can run a negative sign through the whole thing, right? And we end up with this expression here. And let's just clean this up now that we have an expression for H. We're going to go ahead and put the L out in front. And by now some of you are thinking, hey, we can do something here. Let's go ahead and factor out that L. All right. So what we have here is an expression for the height of the pendulum. And that is very useful because it's in terms of the two things we're likely to know, the length of the pendulum and the angle or the displacement of the pendulum, okay? So that's very good, and now we can go ahead and remind ourselves that we're using this in an energy formula for gravitational potential. So we know that the gravitational potential is mgh. So since we now have a new expression for H in terms of L, we can go ahead and make that substitution here, and we can do this right here. And so this is another very important formula, which is the potential energy of a pendulum as a function of the length of the pendulum and the angle of the pendulum. Okay? So yeah, that'll get you through our assignment for today and tomorrow. Hopefully you found this helpful, and I'll be available for additional help if you need it on Google Hangouts via email. I would ask that you don't leave a comment on Shobi if you need help, mostly because I don't get notifications for that. So it's much easier if you just go ahead and email me or send me a message on Google Hangouts. All right, guys, good luck. Hope you